Our eyes, those remarkable windows to the world, can be tricked. Afterimages, fleeting visual impressions that linger after the original stimulus is gone, are a testament to this. They offer a glimpse into the intricate workings of our visual system, revealing how our brains construct our perception of reality. Motion after effects, a related phenomenon, further blur the lines between perception and illusion. After prolonged exposure to moving stimuli, stationary objects can appear to move in the opposite direction. This captivating effect highlights the adaptability of our visual processing. These visual tricks are not mere curiosities. They provide valuable insights into the neural mechanisms underlying vision. By understanding these illusions, we gain a deeper appreciation for the complex processes that transform light into the rich tapestry of our visual experience. From the mesmerizing afterglows of bright lights to the illusory movement of static patterns, afterimages and motion after effects offer a captivating journey into the heart of visual perception. Imagine a spinning disc adorned with alternating black and white segments. As it whirls, your gaze becomes transfixed by its mesmerizing dance. Stare at its center for a minute or so, then swiftly shift your focus to a blank white surface. Prepare to be astonished. A ghostly afterimage of the disc will materialize before your eyes, its colors reversed. The once black segments will shimmer in ethereal white, while the white segments will recede into shadowy blackness. This striking phenomenon, known as the negative afterimage, illustrates the power of afterimages to alter our visual experience. The rotating disc illusion is a classic example of how prolonged exposure to a specific visual stimulus can temporarily alter our perception. It highlights the dynamic nature of our visual system, which constantly adapts to the ever-changing patterns of light that bombard our eyes. By exploring such illusions, we can begin to unravel the intricate mechanisms that govern our visual perception, revealing the hidden processes that shape our experience of the world. To comprehend the magic of afterimages, we must first journey into the eye, where light is transformed into electrical signals that the brain interprets as vision. At the back of the eye lies the retina, a delicate layer of tissue containing specialized cells called photoreceptors. These light-sensitive cells are the key players in our visual symphony. The retina acts like a biological camera, capturing incoming light and converting it into neural impulses. These impulses travel through the optic nerve to the brain, where they are processed and interpreted, allowing us to perceive the world around us. The retina's intricate structure, composed of multiple layers of interconnected cells, plays a crucial role in shaping our visual experience. It acts as a neural processing unit, refining and organizing visual information before transmitting it to the brain. Understanding the retina's complex architecture and the function of its constituent cells is essential for unraveling the mysteries of afterimages and other visual phenomena. Within the retina, two types of photoreceptors, rods and cones, work in concert to capture the vast spectrum of light that illuminates our world. Rods, highly sensitive to light, excel in low-light conditions, allowing us to perceive shades of gray in dim environments. Cones, on the other hand, crave brighter illumination, responsible for our ability to perceive color and fine details. These cone cells, concentrated in the fovea, a small area at the center of the retina, provide the sharp, detailed vision we rely on for tasks like reading and recognizing faces. When light strikes a photoreceptor, it triggers a cascade of chemical reactions that ultimately generate an electrical signal. This signal is then relayed to other retinal cells, including bipolar cells and ganglion cells, which further process the visual information before transmitting it to the brain. The interplay between rods and cones, each with their unique sensitivities and functions, enables us to perceive a wide range of visual stimuli, from the faintest starlight to the vibrant hues of a summer sunset. Section 5. The Afterimage Effect, a Sensory Mishap. Afterimages arise from the fatigue of photoreceptor cells. When exposed to a prolonged, intense stimulus, such as a bright light or a vivid color, the corresponding photoreceptors become overworked and depleted of their light-sensitive pigments. This temporary exhaustion disrupts the balance of neural activity in the retina, leading to the perception of an afterimage. As the fatigued photoreceptors recover, the afterimage gradually fades away, eventually disappearing completely. The color of an afterimage is often complementary to the original stimulus. For instance, staring at a red object will produce a greenish afterimage. This phenomenon occurs because the fatigued photoreceptors for red light become less responsive, while the photoreceptors for green light remain relatively unaffected, resulting in an imbalance in neural signaling that the brain interprets as a green afterimage. Afterimages provide a fascinating glimpse into the dynamic processes of adaptation and recovery that occur within our visual system, highlighting the remarkable plasticity of our sensory perception. Section 6. Motion Aftereffects. When stillness seems to move. Motion aftereffects, like the waterfall illusion, demonstrate the adaptability of our visual system to motion. After gazing at a moving object for an extended period, stationary objects can appear to drift in the opposite direction. This illusory motion arises from the fatigue of neurons in the brain that are tuned to the direction of the original motion. As these neurons tire, their firing rate decreases, leading to an imbalance in neural activity that the brain interprets as motion in the opposite direction. For example, after staring at a waterfall cascading downwards, stationary rocks alongside the waterfall may appear to creep upwards. This illusion highlights the brain's remarkable ability to adapt to prevailing visual stimuli and to recalibrate its perception of motion. Motion aftereffects provide further evidence of the dynamic nature of our visual processing, revealing how our brains constantly adjust to the ever-changing sensory landscape. Section 7. Beyond the illusion, practical implications. While afterimages and motion aftereffects are often perceived as amusing visual tricks, their implications extend beyond the realm of mere curiosity. Understanding these phenomena has practical applications in various fields including art, design, and even aviation. Artists and designers have long harnessed the power of afterimages to create visually arresting works that play with our perception. By strategically incorporating complementary colors, they can evoke vibrant afterimages that enhance the overall impact of their creations. In aviation, pilots are trained to be aware of the potential effects of motion aftereffects, particularly after prolonged periods of staring at instruments or focusing on moving objects outside the cockpit. Such aftereffects can temporarily distort their perception of motion, potentially leading to disorientation or errors in judgment during critical phases of flight. By understanding the underlying mechanisms of afterimages and motion aftereffects, we can mitigate potential risks and harness their power for creative and practical purposes. Section 8. Exploring the world of illusions. The realm of optical illusions extends far beyond afterimages and motion aftereffects, encompassing a vast and fascinating array of visual tricks that challenge our perception and reveal the hidden workings of our brains. From impossible objects that defy geometry to ambiguous figures that flip between alternative interpretations, optical illusions offer a captivating glimpse into the subjective nature of perception. The famous Muller-Lyer illusion, for example, demonstrates how our brains can be fooled by contextual cues. Two lines of equal length, one adorned with inward-pointing arrows and the other with outward-pointing arrows, appear to be of different lengths. Similarly, the Ponzo illusion highlights how our perception of size can be influenced by converging lines. Two horizontal lines of equal length, placed within a pair of converging vertical lines, appear to be of different lengths, with the line closer to the converging point appearing longer. These illusions highlight the active role our brains play in constructing our visual reality, drawing on past experiences, expectations, and contextual information to make sense of the sensory input we receive. Section 9. Conclusion. The enduring allure of afterimages. Afterimages and motion aftereffects, those fleeting glimpses into the hidden workings of our visual system, remind us that perception is not a passive process, but an active construction of the brain. They reveal the remarkable plasticity of our sensory systems, which constantly adapt to the ever-changing stimuli of our environment. From the shimmering afterglows of bright lights to the illusory movement of static patterns, these visual phenomena offer a captivating journey into the heart of visual perception. By exploring the science behind these illusions, we gain a deeper appreciation for the complex processes that transform light into the rich tapestry of our visual experience. So, the next time you encounter an afterimage or a motion aftereffect, take a moment to marvel at the intricate dance of neurons and photoreceptors that brings these illusions to life. They serve as a testament to the remarkable capabilities of our brains, constantly striving to make sense of the world around us.